Hi guys. We are starting Unit 3 in the textbook. It is the unit on light, and we are beginning with Lesson 1, and that is on the electromagnetic spectrum. Alright, so let's get started. First, we're going to actually look at what is light. So in other words, what is the nature of light? And this is what we already know about light from our first unit when we were introduced to waves. We know that it does travel as a wave. It does not need a medium because it is not a mechanical wave. So it does not need a medium to actually travel through space. And it is made of electromagnetic waves. So we know from Unit 1 that light is an electromagnetic wave, and that is in fact a disturbance in a magnetic field. Okay, so let's take that and let's go from there. So we want to know what actually is a light wave. We know it's energy, but we can actually go into a little more detail at this point. So it actually acts as a wave and like a particle. So we know that particles can be charged. These electrically charged particles, they vibrate and they disturb the magnetic or electric field around it. The energy is carried away from the charged particles, and that action of the energy being carried away is what creates an electromagnetic wave. And the transfer of EM waves is called radiation. So, you might have heard of solar radiation before. That is the process of energy being carried away from the sun as electromagnetic waves into space. All right, so let's go back to what we know again. We know that light is a transverse wave, so the disturbances are perpendicular to each other. If you look at the diagram here, all of the blue waves are going, it looks like it's going side to side, and the yellow waves are going up and down. So you have that perpendicular line. And then it says in the caption, it says EM waves travel perpendicular to both electric and magnetic fields. So if the electromagnetic field is going north and south, the magnetic field is going east and west. So it travels perpendicular. And remember, although electromagnetic waves do not need a medium, they do travel slower when they do move through a medium. So light actually travels slightly faster in space than it does once it reaches Earth, when there's air and things to slow it down. Okay, so now we're actually going to talk about what determines the color of light. We see colors, we don't just see bright light all the time, and there's a reason for that. And light comes in colors from red to violet, but what actually makes them different? Well, visible light is a type of light wave, so it has to come in different wavelengths. Some are longer, some are shorter, and we interpret these different wavelengths as different colors. A short wavelength you perceive as violet, and then a long wavelength you would perceive as red. And you can look at the visible spectrum right here. This is actually a segment of the entire electromagnetic spectrum, but the visible spectrum is pulled out here so you can see. So if you see over here, you have your short wavelength of 400 nanometers, that's violet, and then the longer the wave gets, the longer the wavelength, you perceive it as a red color, and that's about 700 nanometers. Okay, so white light is actually perceived when we see all wavelengths of visible light at once. So the eyes register the three primary colors. They register red, green, and blue. Now, this is a little different than your traditional color wheel that you've seen in art, but the main point is all of these combined will give you white light. So white light is actually a combination of all the different wavelengths of visible light, and that's what you see. And all other colors we see are a mixture of those colors. And so we might not see blue in an object because the blue is being absorbed and the green and red is being reflected. So we will see that as yellow. Okay, so there's lots of different combinations that make our eyes see the colors that are out in the world. All right, so now we're going to look at the electromagnetic spectrum as a whole. We're going to, zoom out of the picture a little bit. So electromagnetic waves are measured by frequency or wavelength because they do change. Frequency and wavelength changes as you go across the spectrum. So visible light has a wavelength of 400 nanometers to 700 nanometers, as I showed you in that previous slide. And what we see is only one part of the entire range of EM waves. So we see visible light, but that doesn't mean that's all that's out there. We've talked about this before. We've talked about ultraviolet rays, infrared rays. We can't see them, but they're there. This entire range is called the electromagnetic spectrum. Now, all waves are the same type of wave as visible light, which is a transverse wave, but they're just at a different frequency. So this is the entire electromagnetic spectrum, and this is the tiny sliver that we see. That's the visible light spectrum from about 700 to 400 nanometers. And as you can see, we're going from largest to smallest. So we have radio waves, which is like your AM stations. Think about, when you're driving in your car. You have your FM stations, which are a little bit shorter, and then your TV, and then radar. These are all very, very long wavelengths and very low frequency. As you move into the infrared, it does begin to get smaller. You have 0.01 centimeters, and then it continues to about 1,000 nanometers. As you can see, as we go across here, the wavelength gets shorter and the frequency gets higher. And then we hit our visible light spectrum, which is all that we can see. We move then to ultraviolet, we move to X-rays, and then gamma rays. These three right here, UV, X-rays, and gamma, we know that are very dangerous for us. So it's safe to, conclude that shorter wavelength and higher frequency is usually what is damaging to us as human beings. All right, so here are just some examples. You can find this page in your textbook of what you would see on the electromagnetic spectrum, as well as some examples. So you have your radio waves here. This would cross this entire section of the electromagnetic spectrum. You have your microwaves, and then your infrared is actually over here. You have your infrared light, your visible light, your ultraviolet light, which means beyond violet. So some animals can actually see that because it's very close to our visible light spectrum. So some animals actually can see that. We have our X-rays, and then we have our gamma rays. And you can, go through this in your textbook and read this in more detail, but this does give you examples of all the different types of light. But what is important to see, if we go back and forward as we have this long wavelength, and then this is actually giving you the frequency, okay? And then we have more and more frequent waves as we get across the spectrum. Okay, so I'm going to jump back to what I said before when I said objects can reflect different types of light waves in different ways. So animals who can actually see a little bit beyond the visible light spectrum actually perceive things differently than we do. So take this flower, for example. Humans, we know that we can only see visible light. So we detect this yellow light on these flowers because the yellow light is reflected back to us. However, this would be from the perspective of a bee, and they can see UV light waves. They're shorter than visible light waves, and the flowers reflect UV light back in a different pattern. So it appears that the flowers are different colors when you are viewing it through the spectrum of UV light waves. So just based on what we can see versus what other animals can see, they can look very different. When you think about what bees do when they pollinate flowers, is ability to tell the different colors of flowers is actually, important to their species. All right, so now we're going to focus on how much of the sun's energy actually reaches us. So the sun gives off electromagnetic radiation, most of which is visible light. But the sun also gives off radiation from every part of the spectrum. So yes, most of what comes off the sun is the visible light. However, the sun does give out every type of light on the spectrum. But our atmosphere blocks most of the high frequency waves, which would be UV and gamma. Um, However, oh, well, hold on. The atmosphere blocks most of high frequency waves. I just said that, but lower frequency waves actually reach all the way to the ground. So if you look at this picture over here, this is like the spectrum. You have your radio, which is your longer wavelength, and you have your gamma over here. The atmosphere is this gradient between the black and the blue. The radio and the visible light all reach the ground. However, you have the ultraviolet, some reaches as well, but then as you continue along the spectrum, it does not reach past the atmosphere. So that's actually beneficial for us as a species because this type of light, the short wavelength, high frequency, can damage us. But this is why, we have radio waves and visible light passing through us all the time because it does reach us. But what about this little harmful section right here? What does that mean for us? Well, by that picture, harmful rays do reach the Earth. Ultraviolet rays can pass through the atmosphere. That can cause things like sunburn, skin cancer, it could damage your eyes. So it is important that we protect ourselves with sunscreen, sunglasses, and clothing. We have talked about this before when we were doing our unit on weather. And just like an interesting fact that overheating actually can occur in space. You might assume that the farther back in space you go, it'd be colder. Or if you're not in our atmosphere, there's no way to trap heat. But what's interesting is astronauts actually need to protect themselves from UV rays because in space there is no matter to absorb some of the energy. And we know that waves can actually lose energy due to because it's lost to a medium or because it spreads. So it does make sense that because there is no matter in space, it's actually stronger, though the UV rays are actually stronger. All right, so now we're going to look at how much energy does electromagnetic radiation have. So why are some dangerous and some safe? Why is visible light not harmful to us, but UV rays can cause cancer? So what's the difference? Well, higher frequency waves equal more energy. So a high frequency wave would transfer more energy in a given amount of time than a low frequency wave. So think about it this way. A high frequency wave may transfer 12 waves in a second to a medium, but a low frequency wave may only transfer 3 waves in a second. So the higher frequency wave is transferring more energy in that second than the low frequency wave. So a higher frequency means you're getting more energy to you in a given amount of time. And more energy then equals more danger for us. That is because more energy can actually damage living tissue. Then less energy waves are used in baby monitors and walkie-talkies because it does not harm us because it's low energy. And then on the other hand, you have high energy waves like X-rays and waves. They have to be used with caution. Think of when you get an X-ray, you have like that lead smock that's put over you. That's to protect you from any unnecessary radiation. But when we use things all the time, like baby monitors and microwaves, those are less harmful for us. All right, so you can go ahead and rewatch that if you need to. You can read through this in your textbook. But what you are going to do is you're going to click this link down here when you finish this presentation. And I will actually share this PowerPoint on Google Classroom so you actually can click the link because you can't click it while you're watching. But you are going to take this short, I believe it's about 7 questions. You are going to take the quiz, and then we're going to use your score to determine what type of activities you're going to be doing in class tomorrow. Okay? So thanks for watching, guys, and I will see you in class tomorrow.